Right. So in this D3, we need to understand what are the types of fields are there first. Let's go back and then let's see this basic.
Okay.
So we know there are like three kinds of field: electric field, magnetic field, and gravitational field.
Yeah.
And what caused electric field was the charges, right?
Yeah.
And magnetic field is caused by
Magnet.
like current or a magnet. That's true.
Okay. Yeah.
While gravitational field, we have seen it causes the mass, causes the gravitational field.
Yeah.
Electric field affects charges. What does that mean? So whenever there is an electric field, it affects the charge. So like for example, positive affects the another charge particle, so that attracts.
Yeah.
Magnetic field affects like either magnets or electric current as well. Like we know
Okay.
this.
Okay. Yeah.
Then the like simple positive and then negative charges in north and south pole, but we
Yeah.
have only positive mass. That's the difference.
Yeah.
And we knew like electric and magnetic field is like charges repel, unlike charges attract. Same goes with the like poles repels, unlike
Unlike,
poles
yeah.
attract.
Yeah.
But the gravitational one is always attractive in nature, right?
Yeah. Makes sense.
So if you see, let's understand this electric force and charge moving in electric and magnetic field. So first, charge moving in electric field. So if I ask you to draw this electric field parallel plate, like for example, if this is a plate, and let's call this to be positive,
Yeah.
and let's call this plate to be negative.
Okay.
So this is also known as the high potential
And low potential.
and low potential plate, right? Low
Yeah.
potential. So there will be electric field lines will be generated between them, and that will be from positive to negative and will be going like this.
Yeah.
And electric field lines, they ask you to draw it as well. Okay.
Yeah.
Do it with me.
Yeah, I'm doing it.
And this is inside this plate. Outside it goes a little like this, a little curve, because the medium is getting changed.
Yeah. Makes
around.
sense. Yeah. Okay. Yeah, I got it, sir.
So I need to write down the electric field lines or field strength is uniform throughout.
Is uniform. Okay.
Yeah.
Uniform.
Let's check this. So if I say, let's say the lower potential and then like the bottom one, the negative one, if this is at 0 volt, for example,
yeah,
and above one, like higher potential, let's say if it is at 50 volt, all right.
Okay.
So regardless of whether you place the object at this point or you place it at this point,
yeah,
the electric field strength will remain the same.
Yeah.
All right, the electric field strength will remain the same.
Okay, so electric field strength is uniform throughout. Okay.
Correct.
Yeah.
But potential changes.
Okay.
Why potential changes? Because you can see the bottom one is at 0 potential, right?
Yeah.
If I go slightly above, then potential will be different.
Okay.
Slightly above, the potential will be different. And then slightly above, the potential will be different. And then so on.
Yeah, makes sense.
Okay. Now, let's say if this distance is at 0,
okay.
1, 2, 3, 4, 5, right? I said
yeah.
5, let's say 5 centimeter. So the total distance between them is 5 centimeter. Let's say that, right?
Yeah.
So the value of each horizontal line which I have drawn, so the total potential difference was 50. So each will be like, this will be the 10 volt, 20 volt, 30 volt, 40 volt, and then this is what the 50 volt is.
Okay.
Correct?
Yeah.
So if I say, let's say this is the X and then Y, which one will be at higher potential and which one will be at lower potential?
The higher potential would be the 40 volt. Like
correct. So
X and then
the lower potential will be 10 volt.
Yeah.
Correct?
Yeah.
So if this is a positively charged,
Okay.
X is positive charge, then isn't it will be forced downward, right?
Yeah.
So that's what we're going to say the F is equal to Q times E. You know, the electric field strength is force charge
Yeah.
into electric field strength. That's a
Yeah.
formula.
Okay.
Where Q is the charge and then E being the electric field strength.
Okay, wait.
Electric,
Force is equal. So the vector quantity of the force is equal to charge into the field strength.
electric field strength.
Yeah, okay.
And electric field strength in parallel plate is also related to the potential difference and then distance. So electric field strength is also calculated as potential difference between the plate.
Yeah.
Difference between the plate divided by the separation between the plate.
Yeah, okay. Wait, so what force is this? What
Electric force,
electric force?
electrostatic force, right?
Okay. Yeah. Electric force. Then E is electric field strength. Okay.
Got it?
Yeah.
So there are like two forms which we need to remember. The electric force, the static electric force is equal to Q times E, or electric force is equal to Q times E.
Yeah.
And in parallel plate, it's a potential difference between the plate divided by the separation. Okay?
Potential difference divided by the separate between the plate divided by the separation between plate. Okay, wait. Just one sec, so. Difference between the plates divided by the separation between the plate. Okay, I got it.
Correct?
Separation between plate. Yeah.
So if I understand this, if the charge is positive, it will automatically go along with the electric field lines.
Yeah.
Correct? But if I put a negative charge, so then in that case, work done.
Instead of being repelled, it would be attracted towards the positive.
Yeah, right?
Yeah.
So in that case, it will be the work done will be the charge multiplied by the potential difference between the plate. Okay?
Yeah. The change in potential difference.
Yeah.
Okay. Work done is
Got it?
yeah, I got it. Into the change in potential difference. Yeah. Yeah. Got
So
it.
if
So wait, so this is work done by charge.
work done by electric force,
By
no,
electric force.
electric
Okay. Yeah.
field.
Work done by electric field. Okay. Got it. Yeah.
So if charge is moving in direction of field,
Yeah.
then it will be taken as positive. If it is moving opposite, I mean,
Yeah.
it will be taken as negative. That means, hear me out. Like, if let's say there's a negatively charged,
Yeah.
so negatively charged will like definitely has to go away from it, right?
Yeah.
In that case, you have to push that negatively charged. So let's say if it is negatively charges over here,
Yeah.
you
It'll
have
be
to go in the opposite direction. That will be considered as negative.
negative. It'll be minus work done.
Yeah.
Yeah.
Okay.
Yeah.
And you can also calculate like see the basic general formula. So F is equal to the Q into E, right?
Yeah.
Now the same force can be also written as mass times acceleration, which is Q times E.
Yeah.
So acceleration will be nothing but the Q times E upon mass, right?
Yeah.
So if a proton and electron, so for a proton or electron, or a proton or electron,
Yeah.
which one will have a greater acceleration and why?
Okay. Electron will have a greater acceleration because it has a
Because the
lesser
lower
mass.
the
Yeah,
mass,
lower
right?
mass.
Yeah.
Yeah.
So as the mass is smaller, the acceleration will be greater for that. And I'm assuming that it's in the same electric field and same charge. Okay?
Yeah.
Do you understand this?
Understand. Yeah.
Okay. And we will also see, so if we knew the acceleration, And let's say if this is the positive charge only, and it's starting from rest, okay?
Yeah.
Its initial velocity is 0, and it's starting from rest, and it's accelerating as well, then
Yeah.
will you be able to calculate how much time it will take to reach this negative side of the plate
Wait,
if
so
it
can
is
you
5
just
centimeter
okay,
apart?
wait, yeah, just repeat that once again. So sorry, you cut out. You could do it. Okay.
So I was saying, let's say if this is the positive of the plate
Yeah.
and this is the negative of the plate,
Yeah.
and if the charge Q
Mm-hmm.
starts to move in this direction, which has to cover 5 centimeter,
Yeah. From
will I be
rest.
able to calculate its acceleration according to this?
If you have the mass of it, yeah.
And then we know its initial velocity is 0 meters per
0.
second.
You're trying to find this acceleration.
It's like it has to cover displacement of 5
5.
centimeter.
Mm-hmm.
I'm looking for to calculate
Time.
like no
Yeah.
time, and then acceleration is already been calculated using this.
Okay, so S is equal to UT plus half AT square.
Correct. I can use this SUVAT or kinematics to
Yeah.
solve for that, right?
Yeah.
Did you get this?
Yeah. S is equal to UT plus half AT square. If you use it, you'll get that answer.
Yeah. So another thing which says, let's say if this charged particle is starts moving, so electric field lines are like this, right? Positive
Mm-hmm.
and then negative.
Yeah.
If the charge is thrown into the electric field like this,
Yeah.
so it will always follow the path which is called as the parabolic path.
Okay.
Parabolic path,
So would
because
it just be projectile motion, but with
yeah,
yeah?
you can use all this projectile motions concepts over here.
But so what if the charge is negative in this case?
Then
Would it?
it'll go opposite, like it'll go
Okay.
upward,
Yeah. Fair enough. Okay.
but the path will be always parabolic.
Okay. Yeah.
Okay, and even if you just keep the object into it, like over here, even if the the force is object is stationary or the charge is stationary,
Yeah.
they still exert a little force, right?
Yeah. Okay.
Because the formula says that F is equal to Q into E. It doesn't depends upon this velocity. So
Okay.
even I'll say even if it's rest in electric field, it experience electric force, right?
Yeah.
Got it?
Yeah.
That's a key idea to remember.
So even if it's in rest in electric field, it will still always experience electric force. Okay.
Correct. Because it doesn't depends upon the velocity.
Yeah. Okay. Wait. Let me just write that down.
Doesn't
Even
depends on velocity of the
so,
particle.
even if a particle is in rest in electric field, it experiences field strength.
Yeah.
Electric force. Sorry. Excuse me. Particle. Particle is at rest in E field. It experiences electric force. Yeah, and doesn't depend on velocity of particle. Okay.
Correct. Correct. Okay.
Yeah, got it. Yep.
So you should be able to or do all these work done, potential, electric fields, forces, and its velocity, and then motion as well, right?
Okay, yeah. So you just have to essentially plug in the acceleration formula and then
Hmm.
do SUBAT.
Okay, cool.
Yeah.
Now we're moving on the magnetic field.
Yeah.
So we know the magnetic field is created by current.
Hmm.
So in earlier grades, we have seen that whenever there is a current carrying coil, there is
Yeah.
a magnetic field around it.
Yeah.
So the direction of magnetic field is given by right hand thumb rule, right?
Yeah.
So if you hold the conductor in such a way that the current is shown by the thumb, then all these curled fingers
Yeah.
around the conductor will show the magnetic field.
Yeah. Okay, makes sense.
Okay, so fair enough, right?
Yeah, makes
If you
sense.
if you switch the direction of current to
And
downward,
left. Oh.
then magnetic field will be also opposing. I mean, okay,
Oh yeah, makes sense. Yeah. Okay.
sure, right?
Yeah, just
I
handy.
think you have done this before, so I'm going a little.
Yeah, I've done this.
Then, as you can see, over here.
Mm-hmm.
So if I place a compass at this spot,
Yeah.
okay, then compass will always has this two poles, right?
Yeah.
North and south. So how do we determine the direction of north pole at this point? Let's call it as x. So when you place the compass at point x, okay,
Yeah.
the tangent drawn in that direction will give you the direction of the north pole.
Okay. So at any point, if you draw a tangent, it'll give you the direction of the.
North pole,
Okay,
true.
not okay. Yeah.
So at this spot, if I have to identify the direction of magnetic field, then I'll draw a tangent, and then tangent will be the north pole of it. And so opposite gonna be the south pole then.
Okay, fair enough.
Clear?
Yeah. Hmm.
Then we also need to know or understand this formula. This is called as a magnetic force at a point P due to the current I at a distance R.
Okay.
So use these two examples. So what does it say is that let's say the point P is over here,
Yeah.
which is at R distance
Mm-hmm.
from the magnetic field or like current.
Yeah. Okay.
So its force depends upon directly proportional to the I. Means
The
greater the
charge.
current,
Yeah.
more stronger the
Right.
magnetic field will be, right?
Yeah. More current, stronger field. Makes sense.
Yeah. So this force which I'm talking about, it's a magnetic force. Huh?
Yeah, but so why is it divided by 2 pi r? Why not just r?
So it's like, it's the circle because at the same point it will be over here, over here, over here. It's the same distance, right? It's a
Yeah.
circular path.
Same. Yeah, but so why can't you just use r instead of 2?
So it's a circular path, no? Because magnetic field lines are moving in a circle, right?
Oh, it's moving in a. Oh yeah. Oh yeah. Okay. Okay. Yeah.
All these magnetic field lines are circular path, right?
Okay. Makes sense. So that's
It's
magnetic.
actually mu 0 upon 2 pi is this entire thing as a constant, you can say that.
Okay.
Okay?
Fair enough. Okay.
Where mu 0 is called as permeability of free space.
Well, yeah.
Just like permittivity, there's something called as
Um,
permeability.
Okay.
That's given in your data booklet.
Yeah. All right. Mu 0 into I. It's a constant though, right?
It's a constant.
Yeah. 2 pi into r. This is current. Okay. Got it. Yeah.
Yeah. So whenever there's a current in the wire, there is a magnetic field,
Yeah.
and that strength of a magnetic field is dependent upon,
Yeah.
how much current is running and how far it is. Okay.
Yeah. So this is the magnetic field's strength at a magnetic like the force at a point P at a distance r.
Correct.
And with current I. Okay.
Then how about the solenoid or the current carrying the coil?
Yeah.
So let's say if I have a coil and then the current is running like this, as shown in the diagram.
Mm-hmm.
Right? If the current is going like this manner.
Yeah.
From top to the bottom. Like this. So if the current is passing from this battery to this coil from this way, up to
Okay.
down,
Yeah.
then in that case you have to use a right hand grip rule.
Like that. Okay.
So in right hand grip rule, what you have to do is, if this time the coal fingers, you grip that solenoid in such a way that all four fingers will go in the direction of current.
Yeah. Okay. So just like hold it like that. Okay. Makes sense.
Yeah. And then the thumb will point the magnetic north pole. So if you grip it on this solenoid, then your palm is facing backward, towards your computer, right?
Yeah.
Then the thumb is pointing it to the left.
Okay.
And that will be the north pole created by a magnet. And that would have been, the other side would have been south pole. So magnetic field lines around this solenoid will be again going from north to the south, like this.
Okay. Makes sense.
So this is for the solenoid, the above one for the straight conductor. Okay?
Yeah.
And we expect the greater the current, more the magnetic field lines, and also more number of turns, more the magnetic field strength gonna be. Okay?
Yeah.
Now think about this, the representation of magnetic field lines. So when on these 2D, how do we draw the third dimension? So what we have to do is, we know the right and then left is pretty well, right?
Yeah.
and then up and down is also pretty well. But
Yeah.
what if I have to draw into the page and out of the page, the third axis?
Oh,
So
ZX.
for that, I'm going to use dot and cross.
Okay. Oh, okay.
Imagine if an arrow is coming like this and you are standing over here.
Yeah.
So when the arrow will move towards you, all you will see the front of this dot of the arrow, right?
Yeah.
And when the arrow is like going away from you, you will see the back of the arrow, which looks like a cross to you.
Yeah, makes sense.
So
Hmm.
when I say the magnetic field lines, which is going into the page means going away from me, right?
Yeah, away from you is X across that.
Yeah. And then coming out of the page will be the dot.
Makes sense.
Got it?
Got it. Yeah, got it.
So we also say the magnetic field lines always starts from North Pole to the South Pole, right?
Yeah.
So it's kind of like, the cross gonna be kind of north and then dot will be the south, I mean, like that. Okay?
Fair enough.
Poles. Okay. So based on this,
Hmm.
can I draw this? So let's
Okay.
say if there is a current over here in this,
Hmm.
which is moving up, and how do I identify the cross and dot? So according to right hand thumb rule,
Yeah. So the current would be going from my side, it'll be going from left to right.
so it will be, should I draw the cross over here or should I draw dot over here?
Uh, it'll go toward. You should write dot. It's going towards you. No.
So right hand thumb rule, you're gonna draw, all four fingers will go right into it and comes out from here. No?
Yeah. So
It'll
if
go
it
into and
into
then
the
out.
thing, yeah,
And into the page will be what? Cross or dot?
into the page is cross.
There'll be crosses over
Oh,
here
it's sorry. I was looking. I thought you meant to
and
write
then
the other rule. Yeah.
and then
That's
dot over here, right?
yeah. Okay.
This is how you draw the magnetic field lines. Did you understand?
Yeah. Okay. Wait. Got it.
If I draw the current like let's say this,
Yeah.
then all this, you're gonna hold it like this way. So
Yeah.
it'll
So
go.
it'll be cross at the top and like the bottom and dot at the top. What? Wait. So I'm confused. Because if I'm grabbing it from my screen, I'm grabbing it like from the top, and that's going into the page.
The
Thumb is
thumb will
going.
be going to the right,
Yeah.
and then in the downside, all four
Oh
fingers
wait, you're
will be
grabbing
here.
like this. Oh, sorry. Yeah, I was grabbing it like the other direction. Okay, you're grabbing it like that. Okay, makes sense. Yeah.
So did you get this right?
Yeah. Okay.
Okay. Now here comes this interesting part, which mainly been asked in papers as well. So what is this? This is a magnetic force experience by moving charge, moving charge particle in magnetic field.
Okay.
So what the topic says that whenever there is a moving charge enters in magnetic field,
Yeah.
experience a magnetic force, right?
Yeah.
So do you understand?
Yeah. Okay. Wait. A magnetic force experienced by a moving charge in a magnetic field.
Yeah.
Okay.
So how do we determine it? So here, can we set up a magnetic field, let's say into the page?
Yeah.
So magnetic force on a moving charge particle
Yeah.
in a magnetic field. Check. So I'm gonna draw. Let's say this. I set up a magnetic field which is into the page.
Mm-hmm.
Let's say this. By the way, the magnetic field strength is measured in Tesla.
Tesla? Isn't that this B symbol?
Yeah. So
T,
the
yeah.
symbol is B,
Yeah.
but
The unit symbol is T.
yeah, unit will be the Tesla T.
T. Yeah.
And the MRI thing, right?
Mm-hmm. What am I think? What?
Magnetic resonance imaging technique,
Oh yeah.
MRI.
Oh, the machine. Yeah, I know the machine. Yeah.
So in that they use a really strong magnetic field around 2 or 3 Tesla.
Oh. Oh
So
wow.
if a person has, let's say, implant in his body,
Mm-hmm.
and if he went for iron implant in his body, and if he went for really strong magnetic field, then you get ripped towards his body. I mean,
Oh yeah. Oh yeah.
A
That's
really
like,
strong magnetic field. Okay.
yeah.
Comparatively, Earth's magnetic field is around like 0.005 Tesla.
Oh, that's very small compared to that.
Earth's magnetic field is really small. Okay,
Yeah.
but it's good enough for the still navigation,
Yeah.
right? Yeah. So I was saying that the magnetic force experienced by a moving charge particle. So see, it must be moving. It shouldn't be rest. If
Okay.
it is at rest, that means the velocity will be zero and there will be no force.
Okay.
Right?
Yeah.
What about the charge particle? Which are the charge particles? That could be a proton,
Proton, electron.
electron. Maybe we'll study later alpha as well, and then beta. Beta is same as the electron, right?
Aren't alphas like the helium particles, like the radiation ones?
Helium nucleus, yeah,
Yeah.
true. Okay, true.
Yeah.
But what about the gamma? Gamma do not have any charge.
Yeah.
Charge particle becomes zero, then will be no force.
No. Okay.
Okay,
Yeah. Makes
that
sense.
no force.
Okay.
If it is velocity is zero, that means no force, right?
Yeah.
That's a straight away, like it's saying that. And obviously, if there is no magnetic field, there is no magnetic force as well. Okay,
Yeah.
so let's see. I'm gonna set up, let's say, the charge over here. This is the charge Q, and it is thrown with the velocity v. V
Okay.
meters per second. All right. Do you understand? This is
Yeah. V meters a second. The Q's, yeah, charge is moving through the field.
sure. So when this charge particle enters through it, it won't go Sida. Okay. It'll experience a force.
Yeah.
So when it experiences a force, either it'll go up, down, left, right, or like into the page,
Into the page. Yeah.
out of the page, right? These are the only possibilities gonna be.
Yeah.
So the magnitude of the magnetic force, this F magnetic force is given by this formula, the Q
Yeah.
into V into B
Into
and then
sine theta.
sine theta. Yeah. I've done
Yeah.
this formula in school.
Yeah, we didn't derive it today, they just taught us what it meant today. Yeah.
Yeah. So what is Q over here? Q being
The charge.
the Q is a charge, right?
Yeah.
Charge of that particle. So
Yeah.
as you can see, it's a product, right? If the
Uh-huh.
charge becomes zero, the force is gonna be zero.
Yeah.
And charge is zero for neutron. So if you shoot neutron, okay,
Force will
for
be zero.
neutron, it will go सीधा ऐसे. There will be no force on magnetic force, right?
Yeah.
It will go without any deflected. So the neutron will go without any deflection.
Yeah. Okay.
So there's no magnetic force on that, right?
Yeah.
So v is what the velocity.
Yeah.
So if the charge particle is just simply been kept over here, velocity is zero. In that case, also the force gonna be zero, right?
Yeah.
And then B is what the magnetic field strength.
If that's zero, obviously it'll be force will be zero.
Magnetic field strength, which is also known as magnetic flux density sometimes. Okay.
Yeah.
And then the theta is the angle between.
Wait, but so I don't get how if theta is zero in this case, it's sine.
Okay,
How is force zero?
how the theta will be zero. So theta is the angle between the
Yeah.
velocity and magnetic field strength. Okay.
Yeah.
So right now, what did you notice? Magnetic field strength is going into the page, right?
Yeah. So it'll be 90. Yeah.
And then charge particle is going like this. So the
Yeah.
angle created will be 90, right?
Yeah.
And we know sine 90 is 1.
1.
Okay. But if the magnetic field is also going the same direction and charge particle is also in the same direction. So let me show you
Oh,
here.
then it won't be affected.
Let's say if this is also magnetic field strength and then
Yeah.
charge particle is also moved like let's say this.
Yeah. Okay, it won't be
In
affected.
that case, the theta will be 0.
Makes sense. Makes sense.
Okay. So I gave you the 4 condition in which the magnetic force can be 0.
Yeah.
When charge will be 0, when velocity will be 0, so the charge particle will be at rest. When the
Yeah.
magnetic field strength is 0, so there is no magnetic field strength. And then theta, when it is parallel to the direction of magnetic field. Okay. So this is how you calculate the magnitude of the force. How about direction?
Direction would just be the theta value.
No, the direction of force. The direction of force is given by Fleming's left-hand rule.
Oh yeah, that. index.
Fleming's left hand rule.
Yeah.
Sure.
The
Pakka, you
index,
can.
yeah, the index, thumb, and middle finger. Yeah.
Yeah, I didn't.
Current would be the middle finger. Magnetic field, take the force would be the index, and the what's up again? So field first. Like field would be the index finger, and the force would be the thumb. Yeah.
So I put Fleming's
Yeah.
left hand rule, and as you can see the images, right?
Yeah.
And I'm gonna pick this.
Yeah. So force, motion. Force is thumb. Field strength is index, and middle finger is current.
This one, this is better because I'm gonna use this.
Yeah.
So let's understand this. This is first of all Fleming's left hand rule. I'm gonna use left hand first of all, not
Okay.
the right hand.
Yeah.
Okay. So what this each or like fingers has to do? So the thumb will be nothing but the force or the thrust.
Yeah.
The index finger, okay, or you can see the first finger.
Mm-hmm.
As you
Field.
can see in the first finger, Fi comes in it, right? So that's the
Yeah.
direction of magnetic field.
Okay. Yeah.
So in that magnetic field, this has to be from north pole to the south pole, okay?
Yeah.
And this is the direction of current, the second finger.
Yeah.
So the C comes in, that's a current, right?
Yeah.
Now you know this, right?
Yeah. I know
Whenever
this.
in a wire, if let's say the current is moving in this direction, the current ka direction is same as the positive charge, by the way.
Current's direction is the same as the positive charge.
Yes.
Okay.
But if the electrons are moving, let's say, to the left, then I can say the current is moving into the right because currents are always in opposite direction of flow of electrons or charge, right?
Yeah.
Fair enough?
Fair enough. Makes sense. So if
Okay.
it's a positive, they're moving the same direction. If it's a negative charge, they're moving opposite.
Okay.
Yeah.
So let's say I did not say this Q is positive or negative. Let me just tell you that this is a positive charge.
Yeah.
So the positive charge is moving it to the right. That means that's the same as the direction of current, right?
Yeah.
So according to the Fleming's left hand rule, the current is going in this direction. Okay, do it. I mean, so
Yeah.
you will place the second finger, which is pointing from left to right, index finger pointing into the page,
Yeah.
and then thumb will be going up,
Up.
right?
Yeah. Thumb is going up, index into the page, and the other one
At
towards
this
the right.
point, likely to go up, but it won't keep going up. Huh? Now, what
Okay.
will happen at this point while going it up?
Mm-hmm.
The direction of current is up. The
Yeah.
index finger is over here.
Yeah.
It's likely to go to the left then. Aisa.
Oh yeah, because current. Okay, because okay, current is that way.
And again, it won't keep going like to the right. At this point, the current is in this direction. Magnetic force is into the page, so it's forced like this.
Yeah.
So this kind of make a circle.
So it'll just continuously move.
It continues to move in a circle, right?
Yeah.
So at every point, let's say if at this point, if I take it, that's a direction of current, right? Or the velocity.
Yeah.
The direction of force will be always towards that center.
Okay. Or which was the center of the field, or like the center of that
Center of the circle.
circle. Okay.
At this point, the
Yeah.
charge particle is moving in this direction. That's a velocity slash current, right?
Yeah.
So the force will be to the left, like this.
Yeah. Okay.
At the top, the direction of velocity or the current will be to the left. So the force will be downward. At this point, the force will be to the right. At this
Yeah.
point, the force will be towards like this.
Okay.
Can you recall that which kind of force, which net force acts toward the center?
Which net force? Centripetal force.
Centripetal force, right?
Yeah.
So I'm gonna say that the charge particle, moving charge particle in magnetic field, moves in a circular path,
Yeah.
and that provides a centripetal force. Okay,
Okay.
did you understand this?
Okay. So moving charge particle in a magnetic field provides a centripetal force because it is continuously.
Here, no,
Yeah.
let's look at this. I've written it over here.
Yeah.
So if you consider a charged particle, a proton of
Yeah.
a charge q and moving with a mass m in
Okay.
magnetic field v and then velocity v. I've defined all these variables q, v, v.
Yeah.
Then you can see the magnetic force on the charge is providing the centripetal force, right?
Yeah.
So I'm going to equate them. And magnetic force maximum will be QVB. Why I'm taking QVB and not sine theta? Because I'm taking this to be a perpendicular base.
Okay. Yeah.
Sure.
Yeah. Okay. Wait. You take it. Wait. Can you say the perpendicular thing once? So
Let's say if the proton is moving like from here, okay?
yeah.
So that's the direction of charge particle is like this, and then current magnetic field is oriented to the page. So the angle will be 90 degree.
90. Yeah.
So the magnetic force will be QVB sine theta.
So just one.
Sine
Yeah.
90 becomes like the one, right?
Yeah.
Did you understand this, Pakka?
Yeah. Got this part.
Okay. I'll come back like again over here,
Mm-hmm.
like how to do this. But what happened if I take the same magnetic field, if I set up a same magnetic field
Yeah.
and I instead of proton, I throw this, let's say, electron in it with the velocity v.
Okay. Since it's a negative thing, it'll move in the opposite direction to current, right? So it'll move towards like the front of the. So current will be. Current is going into the, like. So if it moves the opposite direction of the field, if the field is going that way, I'll move out towards me, towards
It
yeah.
will move towards you. Like at this point,
Yeah.
go like this, right?
So
But
yeah.
again, you keep in a circular path, huh? Like
Yeah,
this.
it'll still be a circular path, but it'll go down. Yeah.
Got it, right?
Yeah. Got it.
So the moment will be over here, it'll start moving in a circular path, you can see.
Yeah.
So the direction of velocity of the particle is over here, the velocity of electron,
Yeah.
but the current will be in opposite direction, right?
Yeah.
And
Current
magnetic field is into the page, and hence the force will be towards the center.
center of that point. Yeah.
Okay. Now, hear me out, Aryan.
Yeah.
If I switch the charge
Yeah.
and force gets opposed, right? Opposite.
Okay. Yeah.
If I switch the magnetic field also,
What do you mean
then
switch the magnetic field? So like just make it.
switching the magnetic field means in the sense instead of cross, if I do it dot,
Yeah.
then if you like, let's try this as well. Let's say this is
It'll
a
become
magnetic.
it'll become the same as the first drawing because then it'll move up once again, right?
Yeah, it'll go up like this, no?
Yeah. Yeah.
So by can I say by changing the the charge particle,
Mhm.
by changing the charge particle, right?
Yeah.
Hold on, this moving out of the page.
Yeah, I'll move like that only, sir.
Yeah, correct. No.
Yeah.
So if you just change the the charge, the magnetic force gets reversed.
Okay.
If you just change the magnetic field, the magnetic force also gets reversed.
Okay.
But if you change both of them at the
They'll stay
same
the
time,
same. They'll stay the same.
no effect.
Yeah.
Right? Same.
Yeah. Makes sense.
Got it?
Yeah.
Okay. So that was this part.
Yeah.
And then I can say, can you copy down this this thing?
The definition or the formula?
No, from here. That
Okay.
since it is moving a circular path, the net force will be the centripetal force, right? Which is coming from magnetic force.
Yeah. Okay.
I'm
Mag.
going to equate QVB
Yeah.
to mv square upon r, right?
Yeah.
So write down this.
On charge is equal to centripetal force on by proton.
Then
By
if from here I can make either r as a subject or v as a subject, correct?
yeah.
So if I make r as a subject, the radius traced by that particle, radius traced by that charge particle in magnetic field, that will be mv upon qb.
Yeah.
So for given everything is constant, I can say radius is proportional to the mass of particle.
Yeah.
And it's also proportional to the velocity, inverse proportional to the charge, and magnetic field strength, inverse proportional, right?
Yeah.
So if I'm keeping everything else the same, let's say V, Q, and then B is V, and then B is the same, let's say.
Yeah.
Whose radius is going to be bigger, the proton or electron?
Whose radius will be bigger?
If I shot proton and electron with the same velocity and same magnetic field strength.
Yeah.
So whose radius traced by that will be bigger, proton or electron, and why?
The radius of the proton will be bigger because mass is in the numerator.
Do that, right?
Yeah. Yeah.
Okay. So this way, like from here, I can also make V as a subject. By the way, now
Yeah.
one of the V gets cancelled. So if I make V as a subject, that will be equal to the QBR upon M, right?
Yeah. So the speed of the smaller mass would
Yeah,
increase
correct. In that magnetic field.
in that.
Similarly, we got this. I mean, like it's written over here.
Yeah.
Now think about it. If this charged particle go once in a complete circle in a time t, so the
Yeah.
t being the time period, then can I say the time period is also defined as the distance upon speed?
Yeah.
So the
But
distance it'll be covering in one complete period will be 2 pi r.
yeah, 2 pi r divided by the V formula you got before.
So I got the time period in terms of m, q, and then b, like 2 pi m upon q.
Yeah,
Okay.
in terms of mass. Okay. Yeah.
And the frequency of that charged particle will be 1 upon time period. So you can also do all these.
Yeah.
Got it?
Got it. Makes sense. Yeah, logically. But when will I need frequency, sir, though? I thought that's on waves, no? Uh,
Sorry.
when will I need the frequency, though? Like,
So they'll ask you what will be the frequency of rotation of the charged particle in magnetic field.
okay, so I just do 1 upon the time period.
Yeah.
Okay.
And time period you can calculate like this. Okay.
Yeah.
You
Makes
understood this physics, right?
yeah, makes sense.
You know where this has been used as? Let me show you here. This is called as isotope separation.
Oh yeah, wait, I did a little bit of radiation like last time.
This is also called as mass spectrometer. Mass spectrometer.
Yeah, wait.
Mass spectrometer, what they do? Let's say they set up a magnetic field like this.
Yeah.
Right.
Yeah.
Um, and then from here they shoot the two of the particles, okay,
Uh-huh.
one and then two with the same velocity, but definitely one is heavier.
Yeah.
You know the radius is equal to the qb
Upon
upon qb, right?
QV, yeah. MV upon QV. Yeah.
So the b is the same for both of them.
Mm-hmm.
They shot with the same velocity, same charge as well, because they are isotopes. Isotopes are the
Yeah,
charge will be the same,
yeah.
but masses are different, right?
Yeah.
So if they trace, like let's say this is the, let's
Paths,
say
the parabolic path. Yeah.
with this, and then the shorter one will be traced something like, let's say this.
Okay. Yeah.
So the radius traced by the shorter one will be smaller, larger mass will be greater, right?
Yeah, makes sense.
So I can figure it out which isotopes will have a greater mass or like greater radius.
By tracing the path it will create when you're exposed
Yeah.
to. Okay, makes sense. Yeah.
This is what we call it as mass
Mass spec.
spectrometer.
Okay. Yeah.
Listen,
Makes sense logically.
cool. In the same manner, let's say if there is a current carrying conductor. One last thing, and then we'll stop for today.
Okay. It'll direct the flow of charge, right? A current would just make it.
Yeah. So
Yeah.
now here, the whole idea is magnetic force on a current rather than charge.
Mm.
It's the same thing. Let's say in this setup, I took a conductor. Can you see this? This is the conductor, right?
Yeah.
Like over here. And I placed it in a magnetic field. So you can say South Pole is over here and this is going to be the North Pole.
Yeah.
The magnetic field lines are going from north to south like this. That's why they have drawn this diagram. Okay.
Yeah, okay.
And if I see the current starts from positive, so in the wire it will move like this, correct?
Yeah.
So again, this wire or this entire conductor will experience a force.
Yeah.
The direction of force is given by again Fleming's left hand rule, the same manner, okay? But this time, instead of QBB sine theta, QVB sine theta, I use F is equal to BRL sine theta.
Okay.
Why? Because let's look at this. Because whenever there is a current, there is a charges are moving, right? Isn't
Yeah.
it?
Yeah.
And I'm going to use this little bit of arrangements. I mean, let's say you divide both side by the time and then multiply with the time. Okay.
Yeah.
No effect.
Yeah, none.
So the Q upon T, the charge upon time will be nothing but the current, right? So I'll write down that for the I.
Yeah.
Okay. And then, the velocity
Yeah,
into the time
speed into time is
will be the length,
length.
right?
Yeah.
So that's why it turns out to be B into I into L and sine theta.
Oh, okay. So you just add time, like divide and multiply by time.
Anyway, this formula has also been given in your data booklet.
Yeah.
And again, I'm going to use Fleming's left hand rule only. So this time it's straight away, like you can see, the magnetic field is moving away from me, right? So it's going
Yeah.
north to south.
Yeah.
And the current is moving it to the right. So the magnetic force is coming out of the page.
Yeah, out of the
Right?
page. Yeah.
The force on the current will be out of the page.
Yeah.
And
Field
that
is
is again according to Fleming's left hand rule.
yeah. Magnetic field's going right. Current is coming out of the page and magnetic force is going up.
Correct? Like this
Yeah.
way.
Yeah.
So you should be able to do these things. All right.
Yeah, makes sense. It's not that bad.
Send you the homework. I mean,
Yeah. Send me this.
and I'll
And
send you this notes as well. So
yeah. And can you send me the recording of this class as well, sir?
sure, I'll do that. Okay.
Yeah.
Sure.
Okay. Chal.
That's
Bye,
it for
sir.
today. Bye.
Yeah. So I see you, so have a good day. Bye bye.